These next two practice problems for gases involve the ideal gas law and partial pressures. So question number 5 told us we have a sample of gas where it has 1.45 moles of gas. The gas has a volume of 20 liters and has a temperature of 25 degrees Celsius. And so we are asked to find the pressure of this gas. Okay, so we kind of have been talking about grouping problems into the simple gas law problems where those ones have a change in conditions, and then ideal gas law problems where we just have one condition and we're solving for one of the variables. So this is PV equals nRT, and we're going to solve this for P. So P equals nRT over V. So now we can start plugging in what they gave us. So 1.45 moles times R, 0.0821 liter atmospheres per mole Kelvin, times our temperature. So we have to have 273 plus 25 to give us 298 Kelvin. And then all of this is under our volume of 20.0 liters. So we have moles canceling with moles, we have Kelvin canceling with Kelvin, and then we have liters canceling with liters, and we are solving this in units of atmospheres. Okay, so plug this in, 1.45 times 0.0821 times 298, and then divide that by 20. We have 1.77 atmospheres would be the pressure of our gas. Okay, so before I move on to practice problem number 6, which has to do with gas mixtures, I do want to quickly look at the conditions of STP. So this is sort of a side note. So STP is the standard temperature and pressure. We use this quite a bit in gases. So the standard pressure is 1 atmosphere and the standard temperature is 273 Kelvin. So we do a lot of things at STP where we hold pressure and temperature constant so that we can look at relationships between volumes and moles of gas using Avogadro's law. So at STP, we like to have a relationship, again, between moles and volume called the molar volume at STP. So what this is the volume of gas of exactly 1 mole. So we're going to solve the ideal gas law looking at STP conditions with exactly 1 mole of gas. Okay, so if we do that, we have that the volume of the gas equals N times R times T over P. So 1 mole of gas exactly times 0.0821 liter atmospheres per mole Kelvin times our STP at 273. And all of this divided by our standard pressure of 1 atmosphere. So 1 atmosphere here. Okay, so let's solve that. So we have 1 times 0.0821 times 273, and of course then divide by 1. We get 22.4. So our volume is 22.4 liters, and this is 1 mole of gas at STP. What's nice about having things at STP is we can use this as a relationship to just, if we know, again, the volume of 1 mole of gas, we can solve this for any number of things. So say you're doing a problem and it comes out that you have 0.0479 moles of gas at STP, and we want to know what is the volume. Okay. So if we were given this problem, you could substitute right into the ideal gas law with N here, our T we know as 273 and our pressure of 1 atmosphere. But since we've already kind of done all of this, we can use this relationship right here. So how this works is we can say 0.0479 mole, and then we can build just a regular sort of conversion factor between these two here, and we know that 22.4 liters is for 1 mole of gas. Okay, where our moles cancel, and we can solve for how many liters of gas we'd have. So 0.0479 times 22.4. So we would have 1.07 liters of gas at STP. So again, this only works at STP. If your temperature is not 273 and your pressure is not 1, you can't use this. But we do run gases specifically at STP, so we can use this relationship here. So do look for the words STP, and if that is the case, look for ways to use this molar volume of gases to help sort of lighten the math that you're going to have to do. Okay. So that was sort of a bonus sort of question we did there. Let's go back to the practice problems. So number 6 looks at a mixture of gases. So we have gas A, B, and C. So A, B, and we have gas C. So they tell us that gas A has 0.5 mole. Gas B, 0.25 mole, and gas C, 0.33 mole, and the total pressure is 5.56. So pressure total is 5.56 atmospheres. Okay, so we are asked to solve for the partial pressure of each gas. Okay, so to do that, we need to know the total number of moles, because the pressure of each gas is dependent on essentially its mole fraction or its percent. Okay, so we're going to add all of these together. So 0.5 plus 0.25 plus 0.33, and we have 1.08 moles total. So just adding these together gave us our total moles. So to solve now for pressure of A, pressure of A equals moles of A, so 0.50, divided by the total, 1.08, and multiplied by the total pressure. So it's moles over the total moles gives us the percent, and then times it by the total pressure. So 0.5 divided by 1.08, and then times 5.56. So we have 2.57 atmospheres. So that's our pressure of gas A. So we can do the same thing for B. Pressure of B will be the 0.25 mole divided by 1.08 times 5.56 atmospheres. Or if you look, this is half of this, so its pressure should be half of this, but we can go ahead and solve. But that does work. If you know that this is half, then its pressure has to be half. So 0.25 divided by 1.08 and then times 5.56. We get we'll call it 29 atmospheres. And then finally, pressure of C, we have 0.33 mole divided by 1.08 mole times 5.56, per unit there of mole, times 5.56 atmospheres. Okay, so 0.33 divided by 1.08 times 5.56, we get looks like 1.70 atmospheres. Okay, so these are, again, this right here is essentially giving us the fraction in a decimal form of the gas. So the fraction of the total gives us the pressure of each individual unit here. So if we add these together, so 2.57 plus 1.29 plus 1.70, we get the original 5.56 atmospheres. So those do add up to give us this here. So this is what happens in a gas mixture with our partial pressures.